Swayam Prabha. Digital India. Educated India.
Okay, so we talk about another non-generic attack on block cipher, which is called linear cryptanalysis, and it was introduced by in Eurocrypt 93 by Matsui. So, can you go to the slide, please? Yeah. So, this was introduced in 1993 at Eurocrypt conference, and this was proposed to attack the DES, and but this can be carried out for any other block cipher. We will see how it can be, what is the methodology of this. And this attack can find the DES key, and this is 2 to the power 47 known plain text attack. We know that there are different attack model like one is ciphertext only attack, ciphertext only attack. So, in this scenario, we have only the attacker has only the ciphertext, then the known plain text attack, known plain text attack model. So, here in this scenario, attacker has some plain text and the corresponding ciphertext for some say k many plain text and ciphertext pair. So, this is maybe the earlier communication between Alice and Bob. So, Alice and Bob, they are using this symmetric key encryption. So, this may be some earlier history of their communication. So, this has no relevance now, but now the goal of this model is, now suppose the new plain text is P star. So, goal is to find out the key K or the current message what is being communicating between Alice and Bob. So, this is the known plain text attack. In this scenario, we have the plain text and the ciphertext pair, and we know the other two, one is chosen plain text attack, chosen plain text attack. So, here attacker can choose the plain text and can get the corresponding ciphertext. So, as if we are giving the temporary access to the encryption machinery to the attacker, so that attacker can give their own plain text and can get the. So, this is the temporary access to this encryption machinery. So, attacker can give the plain text corresponding ciphertext. So, there is bit difference between this. This is more powerful, in the sense we are giving more power to the attacker, that we are giving the temporary access of the encryption machinery to the attacker. So, attacker can choose a plain text and get the corresponding ciphertext. So, this is PI CI for certain number of PR attacker can generate, and again the goal is same, goal is to get the key is not revealed to the attacker, goal is to get the key or the current, the new plain text or the new message what is being communicating between Alice and Bob. And another scenario is the chosen ciphertext only attack, chosen ciphertext. So, attacker can choose the ciphertext and can get the corresponding plain text. So, we are giving the temporary access to the decryption machinery to the attacker to this. Okay, so, now we have seen the differential cryptanalysis in the differential cryptanalysis, if we recall, we had to get the, so this is up to, this is the rth round. So it is a, so a typical block cipher is like this. So we have, these are the round function. So dot dot dot. So this is r minus 1th round, and this is rth round, and for each round we need a round key k1, k2, dot 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 k r minus 1 and the kr. Okay, so this is a and these krs, these ki's are coming from the, which you know, the key scheduling algorithm, which is a public algorithm, which is taking the input of the secret key and giving us the round key as many as we need. So for r round we need r round key. For ds, r is 16, and this is for ds, it is a 64-bit block cipher. So this n is 64-bit. So now for we have seen for differential cryptanalysis or differential attack, we consider this to be a function f. This is the function f, and we assume that there is a differential characteristics in this f. So that means this, there is a differential tail in this f. So that means if the input difference is alpha, then the output difference will be beta with some significant probability. So this is also a probabilistic attack. So unless we have this alpha beta pair, the differential trail, then we cannot mount this attack. So then we have seen the attack scenario, like we choose x and then x or alpha, so that input difference will be alpha. Then we have seen the details of this attack, how to get the kr. But this is the differential attack. This is a chosen plain text attack. Chosen plain text attack, because we have to choose the plain text like this, so that input difference should be alpha, to ensure that the output difference here at this stage will be beta. Now in the linear cryptanalysis, it is a known plain text attack. So it is slightly more powerful than the differential attack. Can you go back to the slide, please? So this method, this is a known plain text attack. So it needs 2 to the power 47 known plain text compared to 2 to the power 47 chosen plain text for differential cryptanalysis. And so to understand this attack, we have to use some terminology like what is a Boolean function. So basically Boolean function is a it takes the n variable x s1 s2 sn, and it is giving us a, so it is basically function from 0 1 to the power n to 0 1. Okay. So basically it is a s1 s2 sn. So like if we have a truth table, we can have the truth table for this. These are all binary values. So this is our h. So for different values of this 0 0, we have different values for the output. So this is a typical Boolean function. A Boolean function takes the n bit input and get a 1 bit output. So now a Boolean function is linear if it can be written in this linear form, like a1 x1 s1 XOR with a2 s2, where ai's are basically 0 or 1. It is either 0 or 1. So if this form, then we call this function to be a linear function. So in this linear attack, our aim is to find out the linear relationship between plain text, ciphertext and the key space. We will come to that, and this function is affine function if it is either h of x or it is h of s plus 1. Okay, so this is the set of all affine function we defined. Okay, so this is the idea of this attack. So we have the, so basically it is a block cipher. So n bit plain text and m bit key, suppose m bit key. So this should be capital N. Okay, so this plain text we are writing as P1, P2, Pn, and the ciphertext bit we are writing as C1, C2, C capital N, and the key we are writing as K1, K2 this. So basically we denote this A I j k is basically this linear XOR operation basically. So our aim is to find out this alpha beta, this I1 alpha 1 alpha 2 alpha A and beta 1 beta 2 beta A beta B equal to k gamma 1 gamma 2 gamma A with some probability. So we want to see the linear relationship between the plain text and ciphertext and the key space. So that is the, so this is the block cipher. So we have a key over here. So this is a P1, P2, Pn. So n bit block cipher. You can say small n, and this is C1, C2, Cn, n bit. So these are the cipher. This is the block cipher. It could be DAs, it could be AES, anything. Block cipher encryption. And we have key, k bit key, k1, k2, I mean km. Okay. Now we want to see some linear relationship between this. Suppose we want to see whether this P1 XOR P3 XOR P5 XOR K2 XOR K9 XOR C2 XOR C7 this equal to 0 or not. So that means we want to see some linear relationship between the plain text, key and ciphertext. So in general we can see this XOR with AI PI, this I is from 1 to n, XOR with BI KI, I is equal to k is varying from k is 1 to m, XOR with C we have used. So DI or say alpha I Ci, this I is varying from 1 to n again. So with some probability, with the probability P, and P must be greater than half in order to mount this linear attack on this block cipher. So basically we want to try to get the linear relationship between the plain text. So this AIs and BIs, AIs either 0 or 1, BIs is also either 0 or 1, and alpha is also 0 or 1. So we want to try to get the linear relationship between, then we can have the attack. If we know this linear, then we can we have the linear equations, and then we can try to solve the linear equation to get the key. Key is unknown here, and this is a non plain text attack because we know the plain text and the corresponding ciphertext. If we know some relationship between this linear relationship, and then if we know some plain text and the corresponding ciphertext, that is why it is non plain text attack. Then we have some linear equations, and from that linear equation we can solve this linear equation to get this key. But how to get this such a linear equation? So because this block cipher is having many rounds, so it may be very difficult to find a linear relationship for a long round. So what we can do? So suppose we want to find, so this is say f1, these are the round function. We have k1, k2 like this, fr, and finally. Okay, so here we have some entity. Now suppose for this, so these are all round functions. Suppose we want to see the linear relationship, some linear relationship between in this f1, say some say suppose x1, say xi1, xor xi2, xor xik, xor for this round key, we better use a superscript, say j1, j2, jm xor. Now here this is the output after the first round, and so suppose this is say we denote by y1, so y1 superscript 1. So suppose y k1, k we have used for key, so y l1 xor y l2 xor dot 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 y l some value say alpha prime. So this is 0. Suppose we have some linear relationship in the first round, and again suppose we have a linear relationship in the second round, in for the second round function. So now the question is, this is with some probability. So this is with some probability. Now the question is how we can combine this to get a linear relationship for the whole round. I mean for the this input and the output. Input is basically, so this is the plain text, and after the last round this is the ciphertext. So now the question is how we can have a so we have this small linear relationship throughout the round function. So how we can combine this to get a linear relationship between the plain text and the ciphertext with the round keys. So this is by a theorem or lemma which is called piling up lemma. So we have to understand how it is working, then we will come back to this. So let us talk about piling up lemma. So some probability part we need to okay. So to understand this, let us take the random variable, let x1 x2 dot 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 xi are independent random variable. Random variables. Basically these are basically inputs. Say suppose we have a S box and we have say S box is say m bit to n bit S box. Say. So we have n bits, say this is x1, x2, xn, xm, and we have y1, y2, yn. So this is S box, and we want to see is there any linear approximation for this S box is possible or not. Is there any linear relationship between input and output is possible or not. Okay. So this we are denoting by this x1, x2, so on this input. So these are 0 1 bits. So this can take either value 0 and 1. So the probability of this is the what is called Bernoulli distribution. So this is pi, and probability of xi equal to 1 is 1 minus pi. Okay. So now we define the bias of xi. Bias of xi is basically denoted by epsilon I, which is basically pi minus half. So, that means if pi is half, then the bias is 0. So, this is a truly random bit then. Okay. Now, if pi is not half, then we have a bias, and in that case probability of xi is 0 is basically bias plus half plus epsilon I, and this probability of xi equal to 1 is basically half minus epsilon I. Okay. So, now we want to so this is the bias for epsilon I. Now, we want to know the bias for say this kind of expression x or say simply x1 x2. What is the bias for epsilon what is the bias for x1 XOR x2 or any other thing x2 XOR x4 XOR x6. Okay. So, this bias will give us the linear relationship, or we can have this xi 1 XOR xi2 XOR xik XOR y. Now, we have to bring the y. Okay, yi1 yj1 XOR yj2 yjl say. So, we want to know the bias of this. So, if we can have a bias which is not 0, then we can have a linear relationship between this. So, in general we are looking for this type of expression, this XOR summation of XOR ei xi 1 to m for S box. This is also XOR summation 1 to n bi yi. We want to know the bias for this. If we know the bias, then we can say if the bias is not 0, then there is a linear relationship there. Okay. So, let us calculate this, how we can get the bias for this say x1 plus x2, this kind of expression. So, okay. So, what is the probability of xi equal to 0, x equal to 0. So, we want to know the joint distribution of xi xj. So, this is basically these are independent random variables. So, probability is basically their product pi pj. So, the probability of xi equal to 0, xj equal to 1 is basically pi 1 minus pj. So, probability of xi equal to 1, xj equal to 0 is basically 1 minus pi pj, and similarly this is coming from the independentness of these two random variable xy. So, this is 1 minus pi and 1 minus pj. Okay. So, now we want to know the this is xi XOR xj. So, this is basically a function of this joint random variable xj mod 2. Okay. So, we want to know their probability. So, actually we want to find out the bias probability this equal to 0. When this can be 0? If both are 0 or both are 1. So, this or this. So, this is basically pi pj plus 1 minus pi 1 minus pj. Similarly, for 1 this will be either this or this. So, sum of these two. So, that means, so what is the bias for this? So, if we denote this, so if we denote the bias for this is epsilon 1 2, this is basically 2 of epsilon I1 I2, because this is Ij, I1 epsilon I 1 epsilon Ij is basically epsilon I epsilon j. So, this is the expression for the bias. So, now the general version of this is called piling up lemma. So, the general version of this is basically in general we have this expression epsilon I1 I2 Ik 2 to the power k minus 1 product of epsilon I j, j is equal to 1 to k. So, this is called this is called piling up lemma, this general form. Okay. And this can be proved by induction, because this is true for k is equal to 2, and by induction hypothesis we can assume this is true for k is equal to some m. So, it can be proved that this is true for general m. Now, if all the bias for this xi's are 0, say x I j is 0 for all j, then the bias for this is also 0. So, that means x I1 XOR x I2, this is x Ik. So, bias for this is basically epsilon I1 I2 Ik. So, this will be also 0 if the all biased are 0. So, this way we can use this if the bias. So, this formula we can use to find out the bias in general. So, how we can use this for sorry. So, how we can use this for linear approximation of the S box? Okay. So, basically suppose we have 4 by 4 S box. So, this is x1, x2, x4, y1, y2, y4. Okay. So, basically we will try to see some expression like x1, x2, x3, x2, x4. What is the bias of this? If the bias is not 0, then we have a linear relationship like this. So, this we can just try to calculate from the truth table of this S box. Y2, Y3, Y4. So, we have some values over here. So, this way we can calculate this, try to get the, we can take different AXI, AIXI, BIYI. So, we can take different values of AI and YI, and we can use the piling up lemma to get the bias for this expression. So, if it is not 0, then we have a linear relationship. So, this way we get the for block cipher we try to, so this is F1. So, we try to get some linear biased over here, then here. So, we combine these two by piling up lemma, then finally we should get the bias between the plain text here and the ciphertext and involve some key. So, then we have a linear relationship. If the bias is not 0, then we have a linear relationship or linear approximation. Then we have a, then we can solve this with the unknown key, and then it give us the solution. So, this is the linear attack. Thank you.